Today we are going to discuss our third to the last topic in network laws and theorems, which is the nodal analysis. So in nodal analysis, in AC circuits, it is the same principle in DC circuits. The difference only is that we are dealing here with impedances, and also the source voltages has magnitude and direction. So we will recall our DC nodal analysis. So the node equation method is based directly on Kirchhoff's current law, unlike loop current method or the Maxwell, which is based on Kirchhoff's voltage law. However, like loop current method, nodal method also has the advantage that a minimum number of equations need be written to determine the unknown quantities. Moreover, it is particularly suited for networks having many parallel circuits with common ground connected, such as electronic circuits. For the application of this method, every junction in the network where 3 or more branches meet is regarded as a node. One of these is regarded as the reference node, or what we call the datum node, or the zero potential node. Hence, the number of simultaneous equations be solved becomes n minus 1, where your n is the number of independent nodes. These node equations often become simplified if all voltage sources are converted into current sources. So in nodal analysis, we have, if there are 3 branches meets at any point or at one point, that is what we call the node. One of these nodes here in our example will be our reference node, or the zero potential, or the datum node. So for this equation, or for this circuit, we have 2 nodes. So in nodal, we have the number of equations to be n minus 1. So that will be your number of equations, where your n is the number of nodes. Here we have 2 nodes, so we will only have 1 equation to solve the node voltages of this circuit. Next is that we will assume direction of currents. So I let I1 to be this way, and I2 to the left, and I3 is downward. After assuming direction of currents, we will have our our KCL equation at this node 1. So at node 1, we will let this to be our node voltage VA, and also VB will be our reference node, or vice versa. So this is our equation. KCL at node VA is equal to I1 plus I2 minus I3 is equal to 0. So now, we will consider the direction of current in formulating the equations of our branch currents. So this is our tip. This is the tip of the direction of current, and this will be the tail. So this will be from minus 2. Our Ohm's law is equal to I equal to V over R. So since this is I and I, we will let our branch currents to be in terms of V over R. R is the connecting resistance between the 2 node voltages. Okay, so this is our tip to tail, or from minus 2. Our I1 is from node VB, and it goes to node VA. So that is, for our I1, we have VB minus VA, and our current entered into the negative sign of the source voltage. So that is positive 100 angle 0 divided by the connecting resistance between these two nodes, that is our impedance 1. So 6 plus J8 plus I2. What will be the equation of this? I2 from 2. So from VB minus VA entered into a negative sign of our source. So plus 100 angle negative 60 divided by the connecting resistance is 6 minus J8 minus I3. Our I3 is from VA. So VA minus VB divided by J10 equal to 0. Now, we let our VB to be 0. So, this is 0, 0, and 0. So, the only remaining variable is our VA. Simplifying this equation, we will have negative VA times 1 all over 6 plus J8 plus 1 all over 6 minus J8 plus 1 all over J10. Then plus 100 angle 0 divided by 6 plus J8. Next is plus 100 angle negative 60 divided by 6 minus J8 is equal to 0. So we can now solve the node voltage VA. Negative 0.12 minus J 0.1 VA plus 6 minus J8 plus 9.928 minus J 1.196 equal to 0. So our VA now will be 117.745 angle 9.806 degrees volts. Solving now our branch currents, we will substitute the value of our node voltage VA in each branch currents that we formulated. So for I1, we have negative VA plus 100 angle 0 divided by 6 plus J8. So this now will be your equation, and it is equal to 2.567 angle 178.241 degrees ampere. For I2, substitute VA here, negative VA plus 100 angle negative 60 divided by 6 minus J8. So don't forget the parenthesis in your VA. That is 12.544 angle negative 68.629 degrees ampere. Last one is I3. We have VA divided by J10. So 117.745 angle 9.806 divided by J10 equal to 11.7745 angle negative 80.194 degrees ampere. So you can recheck these branch currents using Kirchhoff's Maxwell and superposition. So for this circuit, we use the nodal analysis.